All right, so I think it's our last lesson in our very short statistics unit is going to be covering the normal distribution. And this is a very brief overview over the normal distribution. We're going to cover what's called the empirical formula and then a little bit of calculator work. We are not going to discuss how to find probabilities under the curve using charts. We're going to be diving into the 21st century together and using technology the entire way. So if you're looking for a lesson that covers how to use charts, you keep looking on YouTube. This is not the right one. So, empirical rule, we're going to talk about what a z-score is and why we used to have to find them all the time. And then we'll talk about how maybe we don't really need to find z-scores too much anymore. And then we're going to calculate probabilities on a normal curve using our TI-84. I'm going to use a CE calculator. So, if we have a normal distribution, which we're hoping in probability land that we have a normal distribution. Sometimes we say like we're assuming that the distribution is normally distributed or the data is normally distributed. That's because if it is normally distributed, we get to use some rules of thumb, if you want to call it that way. So it's bell-shaped, symmetrical, mean in the middle. The mean, median, and mode are all going to be at the central location. So they're assuming because it's normally distributed, those three measures of central tendency are the same. The curve is continuous, it never ends. Never touches the x-axis, and the total area under the curve is 100% because it represents probability, so it has to add up to 100%. So these are some nice graphics from your book, and it shows you some symmetrical distributions, and the one that we're going to be discussing today is that last one there, where it's assuming, because the data is normally distributed, that this probability is going to encompass the entire population rather than just a sample size. There's a rule of thumb in statistics that says the larger the sample size, the more true it is to the population behavior. So at some point, because of the sample size and the data that you see, you just get to assume that you're looking at what the behavior of the population would encompass as far as probability goes. That looks fun, right? That is a fabulous formula that we are never going to use in our class, but it tells you how to calculate the equation of the normal curve. So, have fun looking into that. All right, here's some other visuals from your textbook showing you how having different deviations, standard deviations, can affect the shape of the curve. So, check that out if you want. All right, now we're finally to our notes. This is, I think it's worksheet 12 and 13 in your notes. So, the normal distribution, assuming we have a normal distribution, the area under the curve is normally distributed, it's symmetrical, and it can follow what's called the empirical rule. And the empirical rule is, again, a general rule of thumb that tells you what percent or probability lies between so many deviations off of the mean. So mean being in the middle, if you go one deviation on each side, that is going to cover 68% of the data. If you go two deviations out, it's going to cover 95% probability, or area under the curve is 95% there. And then three deviations out from the mean is going to cover 99.7. So almost the entirety of the curve, but remember it's continuous, so there's no way for us to say it covers the entire curve. We're just going to get numbers that are so small that we just assume it is the entire curve at that point. Because remember, this curve does add up to 100% somehow, even though it never ends. So what this graphic has done for you is it's taken all those probabilities and those area percentages, and it's broken them up into little chunks. So like 68%, they broke it up into a 34 and another 34 because it's got symmetry. And then here's where you have to kind of think about what's really happening here. They broke off the second deviation here and here, but remember that's 95% of the data. So they didn't show this last one, but the three deviations out is 99.7% of the data. So think of it this way. If this big mark here is 99.7% of the data, that means these two little tails cover 0.3% of the data. So if you break that in half, that would be 0.15. So then what they did, this is kind of unusual. You gotta start thinking about this in terms of symmetry though. Remember, from these two red lines, this is 95% of the data. So these two, also small but a little bit larger tails, cover 5% of the data. So the entire amount here is 2.5%, but if you take off this little 0.15%, that is how they got this 2.35. So 2.35 goes from here to here. Weird, right? But the good news is it's symmetrical, so this also from here to here is 2.35. this was 0.15. And these are percents. I should be putting percent symbols after each of these. Percent. Okay. So then, similarly, they looked at the 68% of the data. And when you think about the tails here on the 68% of the data, oh gosh, big golly, what can I subtract? That's 32. So 16. So from here to here would be 16% for these larger tails going out. But if you want to look at just the chunk from here to here, if you took 16% and took away the 2.5%, that's how they came up with this 13.5%. All right. And I think this picture is on your reference page for our class, so you don't really have to do a ton of memorizing. And worst case scenario is you might end up having to develop this empirical rule on your paper if you want to do a whole bunch of problems. But as far as homework goes, I would just look at this diagram. All right, if you want a better looking diagram, oh, it is on the reference sheet. Goodness. If you want a better looking diagram, then you might want to draw one out. Color-coded. I usually, when I first go over these questions again with like Algebra 2 or first time around stats kids, I usually make a really beautifully done color-coded normal curve, which I know it's shocking to find out that I can draw anything that's beautifully done, but I'll be honest, it's not really that beautiful. Okay, so this question is not in your notes, but it's showing you how we can use the empirical rule. So 880 students are in this sample technically, but we'll call it a population. We're assuming it's normally distributed. Has a mean of 67 inches, so they put 67 right in the middle of the curve, and then a standard deviation of 2.5. So they started marking up the curve because of the nature of the next part of the problem, and one deviation up would be 67 plus 2.5, so that's where the 69.5 came from, and then another deviation up would bring them to 72. So the question is, determine the number of students that are more than 72. So they first have to figure out what probability falls in this little tail here. And if you remember that curve, if you go 2 deviations up, from this point on is 2.5%. So then they take the 2.5% as a decimal, of course. That's a 5. And they multiply it by how many were in this population, which is 880. And I'm going to check my notes because I think I already... Oh, it's already done right here. Alright, 22. It's going to be a good day. Alright, this question also is, I think it's from your textbook. It's not necessarily in your notes. Same data? Yeah. So, what percent of students are between 59.5 and 69.5? Well, 59.5 is that teeny 3 deviations out mark, and 69.5 is right here. So, what I would do when I do this question is, I would do the easiest way in my, well, I guess it's not necessarily the easiest way, but I just think of them as chunks. So like 34, 34, 13.5, and this is that 2.35, because we're taking off that little teeny tiny tail. And if you add all those together, apparently we got 83.85. And they went ahead and rounded that to 84%. And they did want what percent of students on that question, so we would just leave it like that. Alright. I know some of you who have some stats knowledge are like, oh man, it's so much easier if we use our normal distribution. I agree, and I'm going to show you how to do that after we do one more question by hand with the empirical rule. Alright, so this question, they want us to sketch the curve. Nailed it. Alright, so we got our mean in the middle, which is 65, and then they want us to go from 50 to 70 with a deviation of 5. Okay, so 1 deviation down, cheapers. It's supposed to be 60. 2 deviations down would be 55. And then, oh gosh, 3 deviations down is 50. Lovely. Gosh, be golly, I'm telling you, they just get worse and worse the more I draw. Alright, 70. So their question is, find the probability, so that's a fancy way of them saying the area under the curve from these 2 blue lines. Okay. A couple of ways we could do this. You could think of it in terms of like half the curve being down this way and taking off this tail. Again, I think it's just easier if you just add up all the little chunks. So this chunk right here is 2.35. This guy here is 13.5. This is 34, and this is 34. And if you were to add all those up, I think I did, got 83.85. Now, remember, the empirical rule is a rule of thumb, and they are not quite exact probabilities, so everything's a little bit off. Those of us who have some stats knowledge, I'm going to go over what we do on our calculator, and those of you who have no stats knowledge, you're just going to jot down some things for me, okay? We could also find the area under the curve between these 2 points using what's called a normal distribution. Normal, but this time we're going to use CDF because it's going to be an accumulation of probabilities between 2 values. So remember, we used to do something with binomial PDF. Well, this is going to be a normal distribution problem CDF. The order that your calculator wants, it wants your lower bound, and then your upper bound, and then it wants the mean, and then it wants the standard deviation. So good news, if you have a newer calculator, you're not going to have to remember this order because it's going to just ask you for all those data values, and then it's going to paste it into the formula. If you're using an older calculator, you're going to need to have this written down somewhere. And I would suggest on our test for class, just use one of my calculators, but it's up to you. So on our calculator, let's see, go to our distribution menu, which is where we found our binomial PDF we've been using in the binomial probabilities, but this time I want the normal distribution. There's a reason it's the first one in the list, guys. It's the most commonly used one in stats class, so the first 2 are. So we're going to use normal CDF because I want it to accumulate all the probabilities between 2 values. Think of it as cumulative. So remember the lower bound, I think the question was 50 to 70, wasn't it? So lower bound was 50, upper bound was 70. My older calculator people, you're just typing these in the exact order that I'm writing them. The mean was 65, and the standard deviation was 5. And then it's going to paste it into the formula for me. Thank you, calculator. And we get 83.99. Now remember, empirical rule was rule of thumb, and they were truncated around a decimal, so it wasn't totally exact. This is the best answer if you're looking for the most exact answer. So if you're going to ask me, well, so what do I need to do on a test? I'm going to expect that you know how to fill out a curve following the empirical rule, and I'm going to expect that you know how to calculate probabilities between values, upper and lower bound. However you find that probability, I frankly don't care. It is ideal that you guys understand the empirical rule, though, because when you go to college and they want you to use strictly the empirical rule, they're going to be looking for that answer, and that's not necessarily the same answer that your calculator gives you, because we saw there's some truncation and rounding issues because of the rule of thumb. So keep that in mind. All right, this question, be careful because the first one says how many trees and the next one is what percent. So it's like that warm-up problem we did that was from your book. So we have 200 trees, so there's your population number, n, and it has a mean of 120 inches and a standard deviation of 16 inches. So just to practice sketching, because apparently I need some practice. That's a little better. All right, mean of 120. And then standard deviation of 16. So if you travel down 16, that's 104. And travel down another 16, that's 88. And if you go another deviation out, it's 72. Yeah, okay. If you go 16 up, I end up at, what is that, 136. You know what, I don't think I need to go any further, so I'm just going to stop. I'm going to put myself out of my own misery here. What are the number of trees that fall more than 136? Okay, so from here up is what they're asking me to figure out. But they want the number of trees, so once I have the probability number, the percent, I need to multiply it by the n. So this mark right here, there's a couple different ways you can do it, but remember we have like those chunks. This guy is 13.5, and then there's a 2.35 plus a 0.15, so I'm just going to call from here to here 2.5, because if you don't stop that tail, it's 2.5. So what does that add up to? 16%, right? So it's 16% times our n of 200, which is 32, right? Yeah, 32. I know, I should be able to do that in my head, but I just can't. All right, what percent of the trees are between 88 and 104? So this time they just strictly want our percentages. So between 88 right here and 104 right here. Well, that's a really easy question because that's one of the chunks from my empirical rule, right? So 13.5. Alright, so that was us using the normal distribution empirical rule. It's an estimation, but it is a good rule, because back in the day when we used to have to use charts to find probabilities and percentages of an area under a curve, the empirical rule was so beautiful because you didn't have to go to the chart. But sometimes the data wasn't necessarily 1 deviation or 2 deviations out. Sometimes we were looking at things like 1.385 deviations out. So that caused us, back in the day, to normalize the distribution by finding what's called a z-score. So we standardized it to a curve where the mean was always 0 and the standard deviation was always 1, using this really simple formula. It's how far the data value is away from the mean divided by how many deviations out it is. So it's a really simple concept when you look at it. Now, as a child growing up where you are now, you're going to find as you travel into stats that z-scores really aren't that interesting to us anymore. Because of our technology doesn't care if you standardize to a z-score, because it can accept the mean and the deviation that you are given. So z-scores really, they aren't necessary for most of our stats calculations. However, it is a concept that's still taught and still pushed pretty hard at the college level. So I want to show you how to find z-scores, and I want to show you what that means for your normal curve, and then take that for what it is. The formula is on your reference sheet, so you don't have to panic about like how to subtract and what order it goes in. It's x minus the mean, so data value minus the mean divided by standard deviation. So this question here, I have some values and they want me to calculate the z-score. They want me to standardize this data value. So the z-score is x, 65, minus the mean. So it's 15 points above the mean, and then we divide it by the standard deviation. So 15 divided by 10 is 1.5. So what that means to us is if we are on a normal curve that we have standardized, now the mean is a 0, 1 deviation is 1, 2 deviations is 2. So they're asking me to find something to do with the probability of 1.5 deviations. And they didn't tell me like up or down from the curve, so I don't know what they want me to do for probability, but what they wanted me to do is find the point on the curve that they're referring to, and they're referring to that point. Now, this is why it's kind of stupid for us to even talk about z-scores, but I have to because of what you're going to see in college. On our actual curve, the mean was 50, and the standard deviation was 10. So this is 60 and this is 70, right? Child, isn't 65 going to land right there in the middle? So it's the same position on the normal curve. It's just a difference of, are you standardizing your data so that you use z-scores and a chart, or are you just keeping your data on the normal distribution with the mean and standard deviation as they were given? All right. So this question is a little more complicated, though, because this is the kind of stuff they ask in college classes a lot. I don't know why. Honest to goodness. They're telling you have a z-score of negative 0.04, and then they give you the mean and the deviation. They want you to go back and find x. So you just plug it into the formula. Negative 0.4 equals, I don't know the x, minus the mean, divided by the standard deviation. So if you think about how you're solving this, you're going to multiply by 5 first, which makes sense because mathematically, you're multiplying the standardized deviation by how big a deviation is for this curve. So I didn't write this down. I think I wrote it down over here. Let me cheat. Negative. Again, I should be able to do that in my head, right? That's a negative 2 equals x minus 40. So then if you add 40 to both sides, we found out that our statistic is 38. Yeah? Yeah. So, I don't know how thrilling those questions are for you, but we're on the next worksheet now, and here we're going to be talking a lot about how to use our calculator. So on a standard normal distribution, this is old school, right? So the mean is going to be standardized to be a 0. Standard deviations are always going to be a 1. It still works the same on our newer calculators. The only benefit is now, I guess if you want to call it a benefit, you can compare two distributions together that don't necessarily have the same mean and standard deviation because you're going to standardize both of them. And the other benefit is you can make your college professors happy who apparently are going to spend tons of time going over this. Okay, here's our normal distribution again, but this time it has that standardization of mean of 0, deviations of 1. So same percentages as before. This is what we used to have to do. We used to have to go find the z-score in the back of a book in a chart, and then we'd have to figure it out by doing that. But good news. Technology has evolved. In fact, when I was a student, we had this technology, and I still had to use a chart for some reason. It really bothered me. So I always checked my answers from the book on the chart. And the problem is the book was never 100% accurate because it had to truncate the decimal. It couldn't fit that many decimals, on a book. So it wasn't always a great answer, and the calculator gave me the best answer. My teacher wanted the book answer, so I had to kind of be careful with what I did. We're going to be using that normal CDF. And remember, if you're using an older calculator, well, we'll talk about PDF in a second. Normal CDF is when you're calculating probabilities between two values. That's the one we used in the earlier example. And I know many of you are either in stats right now or you've had stats in the past. So you are well versed in the normal curve and how to find probabilities on the calculator, because that's a huge, huge standard for that class, right? This question is not in your notes, I believe, but let's kind of talk through what they did. This is from your textbook. So, customer service calls, there's the average number of phone calls was 105, so there's your mean. With a standard deviation of 12, there's your standard deviation. Find the number of days with fewer than 110 phone calls. So what your textbook did is it standardized this data, found the z-score by doing 110 minus 105 over 12, and they found the z-score to be approximately 0.42. So, if you think about your normal curve with a standardization effect, okay, so mean is 0, here's one deviation, so they're asking about 0.42, so like right here on the curve. So fewer than, so they want this probability. Well, it's silly of us, right? Because our calculator, I'm not going to go to a chart to look this up. I'm going to show you two ways we could have done this on our calculator. And I'm probably going to flip back and forth because I can't remember anything. We can pull up that normal CDF again. So it is an accumulation. And when I do lower bound this time, I just need something like significantly low. So if I use their standardized data, anything way low is like, you could type anything negative basically, because remember it's, so usually what people do is they go like negative 99999. Like it doesn't matter. You just, something super, super low down the number line. Sorry, I keep pointing the wrong way. No, that way. All right, so then upper bound, remember we stopped at the z-score of 0.42, I think it was. The mean on a standardized curve is always 0, and the standard deviation on a standardized curve is always 1. And if I paste that into my formula, this is how we would have typed it in the old school calculators, and you would have got 0.663, so 66.3%, which is the percentage. We'll talk about that in a second. But let me show you something. If we skipped that standardization idea, distribution, normal CDF, and I just use the actual data. So if you think about your curve, I already forgot what it was, but the mean was like 105. So if I want something way, way, way down on the curve, I'm just going to type like 1, because that would be way down the curve, right? Upper bound of 110 was the upper bound. The mean was 105. And the standard deviation was 12. So if you think about like having a middle of 105 and then counting backwards by 12s, like 3 deviations down, like you're still going to be at, 70, whatever, something. So going down to 1 for a lower bound is fine. You can still do the negative 99999 thing if you want. It really, honest to goodness, it doesn't matter. But watch this. It's essentially the same answer. It's like 66%. Now, remember, your calculator is doing the most accurate. And if let me change this for a minute. Let me go lower on the lower bound. Negative 99999. Comma. I already forgot what it was. 110. I'm just testing out my theory here. 105, comma 12. Okay. So standardizing your normal curve, you have some truncation there because of the way the math works. If you're also using a chart, like it's not super accurate, And, you know, in the grand scheme of things, is it really important to this question? Probably not. But what they did is they then took the percentage that they found and they multiplied it by the n, which was 30, right? 30-day. Yeah, maybe, yeah. So they found out it was really close to 20, but there were approximately 20 days with fewer than 110 phone calls. Yeah, 30-day month. I see it right there. So I guess I'm giving you mixed messages because I keep showing you the z-score thing because I want you to be able to find them, because maybe I'll ask you to find z-scores. But is it necessary that you use your standardized curve to find the probability? Not really. Some people like to use standardized curves because then they always put in 0 and 1 for the mean and standard deviation, and they don't have to go back and find the problem's data. So that's up to you. All right. This is in your notes again, so let's do a few of these. At a restaurant, the average time between ordering is 12.5, so there's your mean, and the standard deviation of 1.2. Make sure they're both measured in minutes. They are, so we're good to go. Out of 100 randomly selected customers, so there's your n, how many, so after we find the percent, we have to multiply it by 100, will be served within 14 minutes. So basically 14 minutes or fewer. So you are welcome to find the z-score and do it that way. I'm not going to. I'm going to use my normal CDF, and lower bound would be anything really, really small, so like negative 9999. Upper bound will be 14 minutes. Mean is 12.5, and a standard deviation of 1.2. So I think this is already done for me somewhere in my notes. I'm just going to steal the answer. Or not. I'll find it. Just a moment. Alright, so I'm going to steal my answer from one of my coworkers. It came out to like 0.89 something. So if we multiply that by our n, it's about 89 customers. Okay. Again, I do not care if you standardize your data and use z-scores. If you want to, you go right ahead. Alright, so number 5 here. And this might be the last one we do here. Oh, you know, I do have one more topic to cover. Mrs. Kwan, a full professor at the community college, earns a salary of $48,600. The average salary is 52, so there's the mean. Standard deviation of 3,600. So how many of the 45 full-time professors earn less than Mrs. Kwan? Sorry. Alright, so, again, on my calculator, because I think I'm just having one of those days. Normal CDF. I should probably like sketch the curve for you. Maybe during class we will, because then you can laugh at my curve, but I'm done being made fun of on the internet. Alright, normal CDF. I want people who earn less than Mrs. Kwan. So something really, really far to the left negative. I mean, you can go to 0 if you want. It doesn't matter. Your calculator doesn't care as long as it's definitely way, way, way left. So negative 9999. And then Mrs. Kwan earns 52,000. The mean is, oh no, she doesn't. Back up. Read, Abruzzo. 48,600. The mean is 52,000. And then the standard deviation is 3,600. So this on my calculator is coming out to, I'm stealing some work from my coworker. It's like 0.1724-ish. But they want to know how many of the 45 professors fall into this category. So if I multiply it by 45, I get 7.76, which is about 8 professors. So that might be some interesting information to Mrs. Kwan there, that she doesn't make very much money, and maybe she needs to investigate that. Get a lawyer. Alright, during 1 October, average water temperature. Alright, this is getting boring. I'm going to move on. There's a concept right here on worksheet 13. We can actually find the z-scores using inverse norm on our calculator. So if you want to know like where on the normal curve you're falling, you can use what's called the inverse norm, and it is in the, I think, the distribution menu, but I'll have to double check that in a second. So, yep, it is. this question here is find the interval of the z-scores associated with each value. So the middle 50% of the data, and I do think drawing out a curve here would help. The middle 50% of the data, and they want to know what z-scores. So you have to think about what's going on in the tails, because your calculator is going to measure from the left tail down all the time. So if we're looking at symmetry, he's going to find this z-score, and then you'll know this z-score if you do the other tail, but we'll talk. So look at the curve that someone else drew, because it's way better than mine. So from here down, there is 25% of the data, right? So that's what we type in our calculator, the inverse norm of 0.25. But from this mark down, we're looking at 75% of the data. So that's why they typed this one here. And notice, because of the symmetry of the normal curve, your z-score is positive 0.767 and negative 0.67, because that's the middle 50% of the data. So this one's already done for you. Let's try to find something that's not done for you. I think this is the first one that's not done. So this one is not done. So this is on your notes. Number 8, find the interval of the z-scores associated with each area. So on here. Alright, mean in the middle, that's supposed to be the middle. I want the middle 60%. So middle 60%, remember symmetry. So we're talking 30% here and 30% here. So, goodness gracious, I'm so sorry. So this is 60%, which means I have 40% on each of the tails, right? From here down, that's only 20%. Because, remember, both the tails added together is 40%. They're symmetrical, so you got to cut them in half. So then from here down, we're looking at 80%. You could also find that by taking the complement 100% minus the upper tail 20%. Your calculator only reads things from left tail down, so we have to be careful about that. So on our calculator, we're going to do the inverse norm, that's not how you spell norm, of what I just say, 0.2, and then the inverse norm of 0.8, and, oh, I forgot the rest of the, I forget because my newer calculator I think is going to ask me. It's going to want your mean and your deviation and all that, right? So your mean goes next and then your deviation, but if it's standardized because they want z-scores, your mean is always 0 and your deviation is always 1. So this is the nice part about standardizing your curve. You don't have to think about standard deviation and mean very much because they're 0 and 1. On the calculator, distribution menu, we're going to inverse norm this. Okay. So 0.2. No, yes. 0.2. And it's already defaulting to 0 and 1. Probably because my husband just got done doing his stats class, and that was the last time he did a question. And he was using my calculator. So there's our first z-score, negative 0.84. Jot that down. And then we also need to find, let me guess, positive 0.84 when you do the other one. You can, what I like to do is just go back up and edit this guy. But it doesn't, doesn't technically matter. You can go back and retype it. We already knew the answer anyways. Why did I even type it in the first place? Alright, jot down both those z-scores. And just one more. Let's sketch it out first. I think that'll help me figure out what's exactly going on. They want the outside 30% of the data. So they want these two tails to add up to 30%. So these each are going to be 15%. So keep that in mind. And I'm only going to bother finding the 1. So once I find this z-score, this will just be the positive version of that. So if I inverse norm 15%, right? So 0.15, comma 0, comma 1. This apparently is negative 1.03. So this must be positive 1.03. Oh, and you know what? They want me to write an interval. I keep screwing that up. So this interval, you could do like union if you want. For most people, they just say z less than negative 1.03, hello, and z greater than positive 1.03. So down in this interval here, it would have been z between, I forget what the answers were, negative 0.84. So negative 0.84 less than z less than 0.84. All right, I think that covers everything we need to cover. Good luck.